Hello, in 2.7, the rational zero theorem, you will learn to use the rational zero test to determine all possible rational zeros and find all the zeros and factors of a higher degree polynomial. So let's begin by first going over the zeros of a polynomial. If you recall from previous lessons that the polynomial function of degree n has at most n real zeros. And these real zeros can fall into two categories. We have our rational zeros and we have our irrational real zeros. Today we're going to be focusing only on the rational parts of these zeros, how to find the rational zeros. The rational zeros are those that can be written in the form of a fraction. So for example, if we have a polynomial function and all of the integers, all the coefficients, are integers, so these numbers are going to be positive or negative whole numbers, then every rational zero of this function has the following form of P over Q, meaning that we can figure out all of the possible rational zeros by getting the factors of our constant, A sub n, and dividing it by all of the factors of A sub n, which is our leading coefficients. Okay? So let's jump into an example of this. So here we have a polynomial and it satisfies all the conditions. We have a polynomial, again, all of our powers right there. And the coefficients are all positive and negative whole numbers. So I can identify all of the zeros. I can figure out all of the possible zeros, everything that can make this thing equal to zero by getting the factors of our constant, which is this number 12, and dividing it by the factors of our leading coefficient, which is 1. So if I get all of the factors of 12, starting off with 1, the factors of 12 are 1, 2, 3, 4, 6, and 12. 12 divided by 1, 12 divided by 2. Again, my factors are the things that divide 12 without a remainder. So 1 divides 12 without a remainder, so does 2, 3, 4, 6, and 12 in order. Now the factors of 1, the only number that divides 1 without a remainder is going to be 1. Obviously 2, 3, those give you decimal values less than that. So the list of possible rational real zeros is going to be this list of these factors divided by this one factor there. So that's going to be simply the 1, 2, 3, 4, 6, and 12. So out of these 8 numbers, and I say 8, I know that I'm only listing, 12 numbers. I know I'm only listing 6, but I'm considering again the positive and negative. Out of these 12 numbers there, I know that from this list, I can find the 3 factors, or the 3 zeros, the 3 zeros for this polynomial. I know there has to be 3 of them because there's x to the third power from this list. I can find several of them from this list. And for today's problems, they're going to be set up that all the zeros are going to be rational. So here, x to the third power means that we're going to end up again with 3 zeros from this list. They could be all the same number, all positive 1, all negative 1, or all positive 2, or a combination of any of these 12 numbers here, 12 numbers here. So this is again how we get this list of possible rational zeros. So let's do another example. Let's say again, here, very similar, we want to get the factors of our constant 32 and divide it by all of the factors of our leading coefficient 1. So here, again, our leading coefficient is 1, so we're going to divide all of this list by 1. So we're basically going to match up to this right there. So our list of possible rational zeros is simply going to be the factors of 32, since all of those factors get divided by 1. So 1 is a factor, 2 is a factor, 4 is a factor, 32 divided by 4 is 8, 5 isn't a factor, 6, 7, are 5, 6, and 7 are not factors, 8 is a factor, 9, 10, 11, 12, 13, 14, and 15 are not factors, 16 is a factor, 32 divided by 16 is 2, and the last factor is going to be 32. So here's my list of possible rational zeros. Now, let's say that our leading coefficient is not 1. Let's say it's something else, like right here, 4. So again, to find the list of possible rational zeros, we're going to get the factors of our constant, which is 18, and divide it by all of the factors of our leading coefficient of 4. So let's start with 18. And here it is. So here are the factors of 18. The factors of 4 are 1, 2, and 4. So our list of possible rational zeros is going to be these numbers all divided by these three numbers there. So if I start by dividing all of these numbers by 1, then I obviously get the list of 1, 2, 3, 6, 9, and 18. Now I'm going to divide all of these numbers by 2. So 1 divided by 2 is 1/2. 2 divided by 2 is equal to 1, which is already on the list. 3 divided by 2 is 1.5. So 3 over 2. 6 divided by 2 is 3, which again is already on the list. 9 divided by 2 is 4.5. So 9 over 2. And 18 divided by 2 is 9, which again is already on the list, so I don't have to list it again. And then we just do the same thing one more time, but this time dividing, again, all of the factors of 18 by the last factor of 4, by 4. So 1 divided by 4 is 1/4. 2 divided by 4 is 1/2, which is again already on the list. 3 divided by 4 is 3/4. 6 divided by 4 is 2/3. No, I'm sorry, 3 over 2, which is already on the list. 9 divided by 4 is 9 over 4. And then 18 divided by 4, that reduces, 18 divided by 4 reduces to 9 over 2, which again is already on the list. So here's the list. This is a very long list, the list of possible rational zeros. So let's see, try this example. So pause the video and try it yourself. So we'll start by first factoring 10 and dividing it by the factors of 15. The factors of 10 are 1, 2, 5, and 10. And the factors of 15 are 1, 3, 5, and 15. So our list of possible rational zeros, again, divides all of this by every single one of these numbers there. So start by dividing them all by 1. And then continue by dividing them all by 3. Then continue dividing them all by 5. So 1 over 5, 2 over 5, 5 over 5 is 1, which is already in the list, and 10 divided by 5 is 2, which is already on the list. And then divide them all by 15 now. So 1 over 15, 2 over 15, 5 over 15, that's equal to 1/3, which is on the list, and 10 divided by 15 reduces to 5 over 3, which is already on the list. So here is our list of possible rational zeros. Now, the way that we use this is that we use this list again to test possible solutions. Since this is a list of possible solutions, we test the possible solutions again using our factor theorem to determine if those things are possible factors. For example, if x is going to equal to 1, if this is a 0, then that means that x minus 1 will be a factor. So we would use the factor theorem to test again these values and to see if they happen to be factors of this polynomial, breaking it down to a quadratic factor, which then we can use a different technique to factor that. So let me go through the steps on how we use and how we actually find the rational zeros using this. So first, again, we list all of the possible rational zeros using the rational zero theorem, again, this test. We then test these zeros, these numbers, using synthetic substitution. When we find a zero that works, we use what remains, again, the remaining factor, to completely factor the polynomial and find the zeros to those factors. And because we're going to be doing x to the third power and x to the fourth power, that simply requires us to test one or two zeros till we end up with a quadratic polynomial that we can factor using our trinomial, our technique for factoring those quadratics. Either it's a difference of squares or a trinomial. So look, let's jump into an example of this. So let's say we have, again, this example here, and I want to find the zeros of this function. So I'm going to first start by finding all of the possible rational zeros. So possible rational zeros. So I do that by getting the factors of 2 and dividing by the factors of 1. Since I'm dividing by 1, it's not going to change these factors there. So the factors of 2 are 1 and 2. I'm going to divide them, like I said, by 1, so this list is not going to change. So here there's 4 numbers I can test. I could test positive or negative 1, positive or negative 2. Let's start by testing positive 1. Let's check if 1 is going to be a 0. So using synthetic substitution, I have 1, 2, negative 1, and negative 2. I bring down the 1, multiply and add, multiply and add, multiply and add, and I see that since I end up with a 0 right there, that means that x equal to 1 is my 0. So x is equal to 1 is my 0 because my factor is x minus 1. So that is my factor, there's my 0, and again, these things correlate to each other. So by doing this and finding that 1 actually works, what remains down here is a factor of this right there as a quadratic term. So multiplying x minus 1 with this factor of x squared plus 3x plus 2, so multiplying this and this is going to give me this polynomial there. So to figure out the other two factors, I simply have to figure out the factorization of this trinomial. So we use our technique to factor trinomials, quadratic trinomials, which are the factors of x squared, which are x and x, and multiplying 1 with 2 gives us positive 2. So we're looking for the factors of positive 2 that add up to that middle number of 3. So that only combination is if the factors are positive 1 and positive 2. So those are going to be the factors of the trinomial. So the three factors are x minus 1 that I got from testing again, positive 1, x minus plus 2, and x plus 1. So if these are my factors, then that means that my zeros are going to be negative 2 and negative 1. So those are going to be my zeros. And remember, that's the key thing between the factors and the zeros, that if x minus c is a factor, then x is equal to that value of c, the opposite of whatever this number is right there. And vice versa. If x is equal to c, then x minus c is going to be the factor x again, and x minus whatever this number is. So here are my answers. So my zeros again are x is equal to 1, x is equal to negative 2, and x is equal to negative 1. So let's do another example. On this example, we're looking for the factors of 1, and we want to divide it by the factors of 3. And here we actually have to divide because dividing by 3 is not going to keep these numbers up here the same. Well, the factors of 1 are 1. The factors of 3 are 1 and 3. Again, both considering both positive and negative. So the possible rational zeros is going to be 1 divided by 1 and 1 divided by 3. So again, we end up with 4 numbers. So all we have to do now is just simply test one of those numbers. Let's test again positive 1. So multiply and add, multiply and add, multiply and add. So yep, this one worked. So one of our zeros is going to be x is equal to positive 1, which means that my factor for that zero is x minus 1. So we're just missing 2 more zeros and 2 more factors, which we're going to figure out now that I divided this out and I have this factor from this. I have 3x squared minus 4x plus 1. So just like before, with what remains here is a quadratic trinomial that can be factored using, again, our factoring technique for trinomials. So x and x, multiply 1 and 3, which is positive 3. And the factors of positive 3 that add up to negative 4 are negative 3 and negative 1. Now, in this situation, since we actually multiplied by 3, we actually have to undo that. So we're going to divide both of these things by 3. And 3 divided by 3 is 1. So x minus 1 is on the first parentheses, the first factor. And x minus 1/3, I'm going to leave that as x minus 1/3. So my zeros are going to be positive 1 again, because what's going to make these two things equal to 0? Again, the opposite. So x would have to be positive 1, and here x would have to be positive 1/3. So those are going to be my zeros. And if those things are my zeros, my factors are x minus 1, exactly what I have written right here. And for this one, I'm not going to write it as x minus 1 over 3. I'm going to move the 3 to the front. Again, that's essentially I'm going to multiply both the x and the 1/3 by 3, which moves the 3 in front of the x, and minus 1. So I end up with 3x minus 1 as my factor. So again, multiplying these 3 things is going to give me this, and plugging in 1 and 1/3 into the value of x make this thing equal to 0. So there you go. There is your solution. Well, this particularly. We're just doing this part right here as extra practice to understand the relationship between factors and zeros. So let's do another example. Let's do something to the fourth power. So to the fourth power, the same strategy applies. We're just simply going to have to do the synthetic division twice so we can end up with a quadratic trinomial. So let's start by first figuring out the factors of 14, which are going to be 1, 2, 7, and 14. And since the factors of 14 are going to be divided by 1, this list here is also going to be the list of possible rational zeros. So let's try a number from here. Let's try again 1. So we have 1, 7, -3, -19, and 14. And we have 1. This is multiply and add, multiply and add, multiply and add, multiply and add. So again, +1 worked again. Now, we cannot use this factor because this is going to be 1x to the third power plus 8x to the second plus 5x minus 14. And the only way to figure out what makes this equal to 0 or to factor this is factoring it by groups. And I don't want to do that technique where I have to group this, and look for the greatest common factor. No, I don't want to do that. Since I still have numbers that I can choose from this list right here, I'm going to do this technique again, using, again, either the same number 1 or a different number. I feel lucky. Let's see. Let's try +2. Let's see if we get lucky with +2. So I'm going to test +2. So we have 2. This is 10, 20. No, 25. No. So +2 did not work. This is 50. And no, it's not going to give me 0. So +2 did not work. So we're going to have to try something else. Let's try -2. Let's see if -2 works. This is 6, -12, -7, and +14. So there, I found one. +2 didn't work, but -2 does work because I end up with 0. So I found 2 of my zeros. I now know from the first attempt that x is equal to +1, and from the second attempt that x is equal to -2, I'm sorry. So that means that our factors are x -1 and x +2. Again, the opposite. So we're still missing 2 more, and we'll find those by using what remains here, which is going to be a quadratic trinomial, x squared plus 6x minus 7, and using our technique to factor that trinomial. So that would be x and x. We want to find the factors of -7 that add up to 6. Well, since 7 is prime, the only factors are 1 and 7. And since I need a -7, I need to make them different signs. So having a +7 and a -1 multiplies to -7, and having a +7 added with a -1 adds up to that 6. Now, what's going to make this equal to 0? Well, x would have to be -7 in the first factor, and here x would have to equal to +1 in order to make that second factor equal to 0. So there are the other 2 zeros. And given again our 2 zeros, we also have our 2 factors, x +7 and x -1, which again, we knew that from the very beginning because we factored this there. So these 4 things multiply to give us this, and these 4 values will make this function equal to 0 when we replace every single one of these x's by either one of these 4 numbers. And it just so happens to be that 1 is again a multiplicity of 2. There's 2 values where x is equal to 1 twice. or a condition where x is equal to 1 twice, not two values, to condition. All right, let's look at one other example like that, where our leading coefficient is not 1, but it's a 10. So we want to get the factors of 6 and divide it by the factors of 10. Factors of 6 are 1, 2, 3, and 6. And 10 has these factors. So our list of possible rational zeros is going to divide all of this by 1, then by 2, then 3, by 5, and then by 10. Let's start by dividing all of these by 1. And that gives us enough possibilities right now that we can test. If we run out and none of these works, then we'll then divide all of those numbers by 2, and let's see what numbers comes out of that, and we'll test those. But this is a good place to start. So like usual, I'm going to start with 1, and maybe I get lucky enough and 1 works. So let's see. So we have 10, negative 9, negative 24, positive 1, and 6. No, this is not going to work. No, so this did not work. So positive 1 didn't work. So let's try the opposite. Let's try negative 1. This is 5, negative 5. Yep, this one worked. Multiplying, adding gives us 19. Multiplying that with negative 1 is 19. Adding that with negative 24 is negative 5. Multiplying the negative 5 with negative 1 is 5. Adding those is 6. And 6 times negative 1 is negative 6. So yep, that worked. So we have one of the zeros. Now, I want to do this again because this factor here is 10x to the third power. So we would have to do grouping in order to find the greatest common factor, and I don't want to do that. I want to just simply, again, test a different value there. Well, we know for a fact that positive 1 doesn't work, so I'm not going to try positive 1 again. I can try negative 1 one more time. Maybe negative 1 has a multiplicity of 2. But I'm going to try positive 2. Let's see if we get lucky with positive 2. And look at that. Positive 2 is also works. So we found 2 of our zeros. We know that x is going to equal to negative 1 and x is going to equal to positive 2. Which means that in terms of factors, x plus 1 is a factor and x minus 2 is a factor. We're just simply pending the other two that we're going to get by using this remaining factor here, which is 10x to the second power plus 1x minus 3, and factoring that and see what makes each of those factors equal to 0. So here we would start by x and x, multiplying 10 and negative 3, which is negative 30. So we need these factors to be opposite signs that are going to add up to a positive 1. So I need this positive number to be bigger than this negative number to keep that value positive. So that's going to be 6 and 5. 6 times 5 is negative 30, or positive 6 times a negative 5 is negative 30, and then these two things add up to a positive 1. So perfect. Now, because I multiplied by 10, remember that we have to divide then by 10. So that's going to reduce these things to x plus 3 over 5, and this reduces the second factor to x minus 1 over 2. Now, instead of moving again, if I was only looking for the factors, I would multiply this binomial by 5 and this binomial by 2 to move the 2 to the front and the 5 by the front, but I'm not going to do that right now because, again, I'm interested more in figuring out what's going to make this equal to 0. So for the first factor to be equal to 0, x would have to be the opposite of plus 3 over 2, which is negative 3 over 5, 3 over 5. And for the second factor to become 0, x would have to be the opposite of subtracting 1/2, which is positive 1/2. So those are my zeros. And in terms of factors, that's 5x plus 3 and 2x minus 1. So there you go. There's your answers. So those are the variations to using, again, this rational zero test. So we can now, especially when our polynomials get higher order, higher degrees, we need to be able to identify what the possibilities are for that. And for these type of situations, we find those, again, by using this test, this theorem here, the rational zero theorem. But this only works, again, if we have a polynomial and every single one of these coefficients is a positive or negative whole number. If one of them is a decimal or a fraction, then it messes up and this technique will not work. Okay. Well, again, thank you for watching. If you do still have any questions, please send me a message or remind or email. I hope you have a wonderful day. And again, thank you for watching.